In this video we're going to look at pH and what its implications are for the acidity and alkalinity of certain solutions. To start with, I need to look at something called the ionic product of water. So what we know is that water partially dissociates. That means it breaks up into its ions, but only a tiny percentage of water does so. And it exists as an equilibrium state. For more on equilibrium, see the section on chemical equilibrium on the website. As this system is in equilibrium, we can have a look at the equilibrium constant, and that tells us roughly where the position of equilibrium lies. So the equilibrium constant, or Kc for this reaction, is equal to the concentration of the hydrogen ions times the concentration of the hydroxide ions divided by the concentration of the water. We can easily calculate the concentration of water because water has a density of 1 gram per centimeter cubed, so therefore there's 1000 grams in a litre. If there's 1000 grams, then there's 1000 divided by the mR of water, which is 18, 55.55 moles. So now I'm just going to rearrange the equation above by bringing this up here. So multiplying both sides by the concentration of water, and we get Kc times the concentration of water is equal to the concentration of the hydrogen ions times the concentration of the hydroxide ions. But because we know that the concentration of water is pretty much a constant and Kc is a constant, we're just going to equate that to a new constant and call that constant Kw. So Kw, or the ionic product of water, is equal to the hydrogen ion concentration times the hydroxide ion concentration. This actually can be measured experimentally. At 25 degrees, it's found to be about 1 times 10 to the minus 14. So Kw is 1.00 times 10 to the power of minus 14 mole square per dm to the power of 6. 25 degrees. Because the Kw changes as temperature changes. For example, if the temperature goes up to 50 degrees, the Kw increases to about 5.5 by 10 to the minus 14. So just to recap, equilibrium constants only remain the same at the same temperature. So if we change the temperature, we change the equilibrium constant, and therefore in this case we change Kw. As we know that the concentration of hydrogen ions is going to be equal to the concentration of hydroxide ions for a neutral solution, what we can say is for a neutral solution, H plus squared equals 1.00 times 10 to the minus 14. So H plus concentration equals 1.00 times 10 to the minus 7 at 25 degrees. This is because in pure water we have equal amounts of H plus ions and OH minus ions. So for a neutral solution, the concentration of H plus ions is going to be equal to 1 by 10 to the minus 7. So remember, for all solutions, Kw is equal to the concentration of the hydrogen ions times the concentration of the hydroxide ions. So let's have a look now and see what happens when we add acid to the solution and what happens when we add alkali. If we add acid to the solution, we know that the value of Kw cannot change. So if Kw equals H plus by OH minus, which is equal to 1.00 by 10 to the minus 14. If I add acid into that solution, Kw won't change. So what's going to change? Well, the concentration of OH minus is going to decrease. This is because when I multiply the new concentration of H plus ions times the concentration of OH minus ions, it must be equal to 1 by 10 to the minus 14, because Kw is a constant at a constant temperature. Likewise, in an alkaline solution, the concentration of OH minus ions increase, so therefore the concentration of H plus ions decrease, so as to make the Kw equal to a constant. So in summary for that, Kw controls the balance between the hydrogen ion concentration and the hydroxide ion concentration in all aqueous solutions, and relative concentrations of each are determined by the Kw. As we know that that's constant at constant temperature. So if we look at a scale, we know that when H plus equals 10 to the minus 7, we have a neutral. And if we go to the right, we have an alkaline solution. So H plus ions will decrease as the OH minus ions are increasing. So H plus here are going to be less than 10 to the 7 minus 7. And on the left hand side we get more acidic solutions, and the concentration of H plus ions is greater than 10 minus 7. So just to put a scale on that, this is our H plus concentration, and here we have 1, here we have 10 to the minus 14, and here we have 10 to the minus 7. I'm just going to recall that 10 to the 0, which is just 1. So that's a scale that shows the hydrogen ion concentration. Now, we don't usually quantify an acid by just the concentration of hydrogen ions because the numbers are so small. So what we do is we convert them to a logarithmic scale called a pH scale. So the pH of a solution is equal to minus the log of the hydrogen ion concentration. And if I look at the scale above, I'm just going to write pH for each here. And if I calculate the pH of, let's say, the hydrogen ion concentration here, I would get a value of 0. If I calculated the pH of the solution here with this hydrogen ion concentration, I get a value of 7. And if I calculated the pH of this concentration, I would get a value of 14. So this gives us a better indication of where the pH scale actually comes from. From 0 all the way up to 14 there, we have a hydrogen concentration of 1 down to 10 to the minus 14, which is obviously very, very small, and an alkaline solution. So we have an acid pH, which is less than 7, and an alkali pH, which is greater than 7. Remember, an alkali is just the source of OH minus ions. So, for example, if my solution had a hydrogen ion concentration of, let's say, H plus concentration was equal to 1.22 by 10 to the minus 3 moles per decimeter cubed, if I plug that into my calculator, I'm going to get a pH equal to 2.91. So it's really straightforward for strong acids because they fully dissociate. You take the hydrogen ion concentration, because for every concentration of the acid, let's say this could have been concentration of HCl in a bottle, that gives me a pH of 2.91 because I was able to take the concentration of HCl being the same as the concentration of hydrogen ions, because full dissociation here. But it changes for a weak acid because of the fact that a weak acid exists in an equilibrium whereby only some of the molecules have dissociated. So we're going to look at that now. So for weak acids, we know that the acid itself, when added to water, will dissociate into H3O plus and A minus, but because there's not full dissociation, we can set up an equilibrium, and if I want to calculate the equilibrium constant, Kc, it will be equal to this concentration times this concentration over this concentration times this concentration. But what we can now look at, because we know the concentration of H2O isn't going to change much, we can convert that into what's called an acid dissociation constant, Ka. Ka is equal to concentration of H3O plus times the concentration of A minus, all divided by concentration of HA. So what we know is, at certain temperatures, weak acids will always have a certain Ka, acid dissociation constant. For example, the Ka for ethanoic acid is 1.8 by 10 to the minus 5 at room temperature. So what we know is that weak acids are going to have a fairly low Ka. While this is not on the Leaving Cert course, we can look at another thing. If I actually look at Ka and took minus the log of Ka, that's something called a pKa. Now, all weak acids have a pKa. Actually, most substances have a pKa, and they will tell you how acidic the substance is. But fear not, that is not on the Leaving Cert course, but it's a really useful piece of information, pKa. So we know that the smaller the Ka, the weaker the acid. Therefore, the larger the pKa, the weaker the acid. We're now going to look at how to calculate the pH of weak acid. We're going to go back and have a look at the acid dissociation constant for a weak acid. So now we're left with Ka equals H plus squared over HA Now if we're looking to find the pH, we need to know the hydrogen ion concentrations, so I rearrange this equation to isolate H plus on its own. So I multiply both sides by concentration of HA here. Well, Ka times concentration of HA then is equal to H plus squared. Then I'm left with taking the square root of both sides and just rearranged H plus to keep it on the left. H plus concentration is equal to square root of Ka times the concentration of HA, which is the concentration of the weak acid. So if I wanted to know the pH of a certain ethanoic acid solution, I'd need to know its concentration and I'd need to know its Ka, acid dissociation constant. So let's say, for example, I had a solution which was 0.100 mole per dm cubed. And let's say I know that Ka at 25 degrees is equal to 1.8 by 10 to the 5. I'd work out the H plus ion concentration, which is equal to root 1.8 by 10 to the minus 5 times 0.01, which is equal to 1.319 by 10 to the minus 3, and pH therefore is minus the log of this, which equals 2.88. So just to compare, that's got a pH of 2.88 with a concentration of 0.1. If I went back up to my strong acid calculation here, when we had a strong acid but only a concentration of 1.22 times 10 to the minus 3, which is 0.00122, that concentration gave me a pH which was similar enough. Okay, so there we have it. The strong acid has a certain pH. It can be equal to that of the weak acid, but the concentration of the solution is going to be vastly different. Here the concentration of the solution was 0.001, whereas here it was 0.1, so there's 100 times the difference there in the concentration.